In this demonstration, I'll be showing you how to create a MicroBlaze and Ethernet based application on Xilinx Artix FPGA evaluation board. I'll be using FreeRTOS operating system and lwip IP stack in this demo. This is the hardware and software which I'll be using for this demo. I'm using a Xilinx AC701 evaluation board. It is an Artix FPGA based evaluation board. Artix is a low-cost FPGA in the 7 series FPGAs of Xilinx, and I'm using Xilinx Vivado and SDK 2018.1 version for this demo. In a previous video, I have shown how to create a simple UART-based application for a MicroBlaze processor. The steps involved in designing an Ethernet-based application is identical to what we have done in the previous demo. The only difference will be the modules which we are adding in the IP integrator during the hardware definition stage. So the first step is to define the hardware configuration which will be used for programming the FPGA fabric. As you know, Artix 7 FPGA is a complete FPGA fabric. It does not have any built-in hard IP blocks in it. Whichever blocks are required in your design, you have to manually add the soft IP core, and accordingly the FPGA fabric will be configured. So you have to define all the modules which are required for your application in the Vivado IP integrator during the hardware configuration design phase. In the second phase, we will be synthesizing the design which we had defined in the first step, and we will also generate the bitstream file which will be used for configuring the FPGA. Then this design will be exported to the SDK for developing the application software for running on the MicroBlaze processor. After that, we will be developing the actual application which is based on FreeRTOS and lwip IP stack, which will be running on the MicroBlaze processor. That is the fourth step. And in that step, we will be generating the executable file which is in the ELF format. And in the fifth step, we will be configuring the FPGA and running the application. We will use the bitstream file which we generated in the second step and the ELF file which we created in the fourth step to run it on the MicroBlaze processor. So these are the 5 steps involved in the design of this whole demonstration. So let's get started. We'll move into the first step, which is the design of the hardware configuration, which we will be doing in the Vivado IP integrator. So we'll go ahead and create a project in the Vivado. So now Vivado is started. I'm going to create a new project. Click on the create project link. Here you can click next and select the folder where you want to create the project. And here you can select the RTL project. And since we are not developing any STL program, we need not select any file here. And in this part selection window, you have to select the boards. Since I'm using the AC701 evaluation board, I can search for AC701. And this is the evaluation board which I'm using. So I can select that and click next. And then I can click finish to create the project. The project creation is completed. We will go ahead and start the hardware design based on the IP integrator. So in the IP integrator tab, you can select the create block design and click OK. Now we are ready to start the hardware design process. If you are new to MicroBlaze based design, I would recommend you to go through the previous video in which I'm explaining the MicroBlaze memory organization. So as I mentioned there, MicroBlaze requires some memory for executing your application. We can create some amount of RAM within the FPGA itself. As we have seen, we can configure a maximum of 128K of RAM using the block RAM cells available in the FPGA itself. And in the previous demo, we have executed our application program from that local RAM itself within the FPGA. So we were not having any external memory. outside the FPGA. But in this case, since we are going to run a Ethernet based application using FreeRTOS and lwip stack, our application will not fit into this 128K RAM within the FPGA. So we have to go for an external memory. The AC701 board is having a DDR3 RAM on the board itself, so we can use that RAM for executing our program. So the first step in the hardware design is to add a memory controller, the DDR3 controller, which will allow us to access the RAM memory present on the AC701 board. So either you can generate the DDR3 controller by directly adding the memory interface generator IP, or since you are using a standard board, an easier method will be to select this board tab here, and here you can see the resources of the board. And as you can see here you have an external memory resource of DDR3 SDRAM. So you can just select that and drag it onto this diagram window. It will automatically add a memory interface generator there. The memory interface generator is added by Vivado. Just click OK, and now we can generate the memory interface using this interface generator, which has been automatically added by Vivado. You can just double click on this to start the generation of the memory module. So this is a window for configuring your memory interface generator. There are a number of steps involved in creating this memory interface. Since you have selected the board resource of the AC701 from the board tab, it will automatically fill all the details corresponding to that AC701 board into this memory interface generator inputs. So you just have to go through all the steps of this. You need not edit anything, or everything will be automatically filled by Vivado. So you can just click next. So in each stage it will be asking for certain inputs which has been already set by Vivado. So you can just go through everything. Click next. So you can see DDR3 interface is selected. The memory part number and device number, everything is selected here. The extra user interface clock is also defined. Now here the pins of the memory modules are also defined. If you are not using the standard board part, you have to manually fill the pin numbers of the FPGA which is connected to the DDR3 RAM. Since we are using the AC sensor on board, all the pins are automatically populated by Vivado. You just have to validate it and check. You can proceed. You click the validate button. So the pinout is valid, so you can click next. So this is a summary of whatever selections we have done so far. Click accept here and click next. And finally you click the generate button to create the memory interface. Once that is done, you can go ahead and do the connection automation here, so that Vivado will automatically connect some of the pins directly to the board resources. We can maximize this window. Now the memory interface is created. Now we can go ahead and add our MicroBlaze processor. So just press this plus button and search for MicroBlaze. So you have the MicroBlaze IP core here. Just double click to add it. So now the MicroBlaze processor is added. So Vivado will automatically offer us run block automation. So you can click on block automation. So as I mentioned earlier, In this case, we will be using external memory to run our application. In the previous demonstration, we have run the application from the local memory within the FPGA itself. So here we have the option of selecting the local memory. In the previous demo, we have selected 64 KB so that we can run the application from that memory. So as you can see, 128K is the maximum, which will not be sufficient for our Ethernet based application. So we will select 64K and we will not be using this memory. So in case if you are finally putting this application on your board, you will require this local memory for generating the bootloader application for your design. So other than that, everything you can leave it as such. Since you are adding number of peripherals, you will be requiring this interrupt controller. So enable this interrupt controller and then click OK. Vivado will automatically add all the additional IPs which are required for the basic functionality of the MicroBlaze IP core. The block automation is completed. We can also do the connection automation. So all these blocks has been added by Vivado. I have already explained each of this block in the previous video. We can go ahead with the connection automation as well. Select all the signals here and click OK to do the connection automation. Now the connection automation is also completed. Now we can go ahead and add our peripherals which are required for our application. So in this case, since we are adding going to use a FreeRTOS operating system, we will require a timer in this design. So we have to add a AXI based timer here. So just click the plus symbol and just search for timer. So you can see an AXI timer IP core here. Just double click on that. So the AXI timer is added. You can run the connection automation to connect the AXI signals to the AXI interconnect. The AXI interconnections have been completed. We will also add one UART for printing the debug messages. So this is the same UART which we used in the previous demo, AXI UART. So just double click on that and run the connection automation to connect both the AXI and the UART related signals to the external ports of the FPGA. So now all these signals have been connected. So as we can see here, since we have enabled the interrupt, Vivado has added the interrupt controller and input concatenation unit. By default, it is showing only two interrupt inputs. Based on our number of peripherals which we are adding, which we want to connect it to the interrupt controller, we have to decide the number of inputs required. So now we have already added AXI timer and the UART. We will go ahead and add the rest of the peripherals and finally we will decide the number of inputs required. So the next peripheral which we require is the Ethernet. So for Ethernet again, it is easier to use the boards tab of the AC701. On the AC701, there is a Ethernet connector and an external Ethernet 5 chip is available, which is connected to the FPGA. The FPGA to Ethernet 5 connection is done through the RGMIA interface. So we can just select this onboard 5 interface, which is shown under the Ethernet configurations selection. You can just select that onboard 5 and drag it onto the diagram window to add the Ethernet controller. So it will be adding the Ethernet soft IP core for this design. Now this IP core has two modes of operation. One is the DMA controller based operation and the FIFO mode of operation. For this demo, we will be using the DMA controller because since we are using the MicroBlaze processor, it is easier to implement the DMA based mode. So the block has been added. So you can go ahead and do the block automation where it will automatically add the DMA controller required for the Ethernet operation. Just click on the block automation. So as you can see here you have an option of selecting DMA or FIFO. So we will leave it at DMA option. so that Vivado will automatically add the DMA controller. Now the DMA controller and the Ethernet IP are added. So as you can see, this is the Ethernet IP, AXI 1G 2.5G Ethernet subsystem, and AXI DMA controller has also been added. So you can just run the connection automation so that the AXI signals and some of the clock inputs will be automatically connected by Vivado. So now all the peripherals have been added. Now, as I told earlier, we have to manually connect the interrupt outputs of each of the peripheral to the interrupt controller which has been added by Vivado. So if we see, we have an AXI UART and an AXI timer here. Both are having one interrupt output, and we have also added this Ethernet and the DMA controller. So Ethernet has an interrupt output, and the DMA controller has two interrupt outputs. So altogether we need five interrupt inputs for this design. So we have to configure the interrupt controller so that it can take five inputs. So just double click on this interrupt input concatenation unit, and change the number of ports to 5. So now you have five inputs for your interrupt controller. You can go ahead and connect each of these interrupt lines. First we will connect the Ethernet interrupt. This is the Ethernet interrupt line. We'll connect it to the first input of the interrupt controller, and then we have two interrupt output from the DMA system. So we'll connect both of them. Connecting it to the third input. Now we also have the AXI timer and the UART. So we'll connect the UART. So UART interrupt input is connected, and we will also connect the timer interrupt input. The timer interrupt also has been connected to the fifth input of the interrupt concatenation unit. Now all our hardware connectivity is over and all the blocks have been added. You can save this design by clicking the save button. Now we need to create a STL wrapper for your entire hardware design. So go ahead and create the STL wrapper. For that, go to the sources tab and select the design one, which is the name of the design which you have created, and select the create STL wrapper option, and we'll let Vivado manage the wrapper automatically, and click OK. The STL wrapper creation is completed. So now we have completed the step one of our design. Now the next step is to synthesize and generate the bitstream file for configuring the FPGA. So we have to go through the synthesis, implementation and bitstream generation processes. So if you directly execute the generate bitstream option, it will automatically do the synthesis as well as implementation also. So I think we have added all the peripherals required. Now we will go ahead with the bitstream generation. Here I am selecting three tasks. You can select the maximum number of cores available on your PC. if you are not planning to do anything parallelly on your PC. Since I am doing the screen recording, I am selecting 3 and click OK. This will start the compilation process. So we have added a number of modules here. So the compilation, first time compilation, Vivado has to compile each of the IP we have added individually. So this is going to take a long time. The second time onwards, when you are compiling, it will compile only the module which has been changed. The first time the compilation will take a considerably long time, especially the memory interface generator. So I'll pause the video and come back once the compilation is completed. So the bitstream generation is completed. It has taken close to 2.5 hours on my machine. So we have completed the second step of our design. So the synthesis and generate bitstream step was completed. So we will move ahead to the next step, that is exporting the hardware to the SDK. So for that, go to the file option, then export hardware, and include the bitstream file which we have created in the previous step, and click OK. Now the hardware is exported to the SDK where we can generate the application program. So next step was to develop the application program which we will be doing in the SDK. So we have to now launch the SDK. So go to the file and we can launch the SDK from here and select OK. So now it is starting the SDK. Now the SDK is completely started. So this is the hardware configuration which we have exported from the Vivado, and this is the bitstream file which we have generated. Now we'll go ahead and create the application program for running on the MicroBlaze processor. So go to the new and select application project. So in this case, we are going to create an application program using FreeRTOS operating system, and we will try to select an lwip IP stack based application for this. So give some name for your application project, and here you can see the default selection as standalone. So we will change that and select FreeRTOS. Xilinx is supporting the FreeRTOS by default, so you can just select that to get a FreeRTOS based application. And we'll create a new BSP since nothing is existing already, and select the next to select the sample application template. So we will select a FreeRTOS LWIP echo server. That's a simple program using the LWIP IP stack. So the good thing is Vivado will automatically, the SDK will automatically configure all the parameters of LWIP for using this echo server application, and just click finish. So by default, this echo server, what it does is it configures the Ethernet port on the FPGA board, and it will start a small application there, which you can connect to that application from your PC through a application like your Teraterm or Putty, etc. So now it is building the application. So as you can see on this side, it has created a BSP folder as well as the application folder. Inside the application folder, you can see the source file for the application which it has created. And by default, the SDK will be creating an application which will be looking for the DHCP server for assigning the IP address. So we can actually modify that to assign a static IP address. So wait for the workspace to be completed, then we can go ahead and change the BSP settings. So there you can see all the configurations of the LWIP stack as well. Now the process of building the workspace is completed. I don't want to use DHCP for our design, so I'll just modify the setting. You can click on this modify BSP settings and select the LWIP library here, and here you can see the DHCP options. So they have configured it as true. Both of these options you can change it to false. The LWIP DHCP and DHCP ARP check both can be selected as false, and then you can click OK. SDK will automatically recompile the BSP, and it will also regenerate the application program. So wait for that to be completed. You can see the progress in this console window. It is compiling both the BSP as well as the application software. You can also take a look at the application program which it has created. So this is a simple FreeRTOS based application. You can modify this to create your own application. This is the starting of the FreeRTOS scheduler, and different threads are created, and since we are using LWIP, we need to use specific functions which are related to LWIP. New threads has to be created using this systhread new function when you are using LWIP. So you can take the sample template and modify this application as per your requirement. So for our demonstration, we'll be simply using the same application which it has created, and we will download this application into our evaluation board, and we will try to check the Ethernet link, functionality of the Ethernet link, by sending a ping request from our laptop to the evaluation board. So before configuring the evaluation board, you have to connect the evaluation board to your PC. So for this demonstration, we require 3 connections. One is the JTAG connection, one cable for the JTAG connection, and one for the serial port, that is the UART messages, and also you have to connect the Ethernet connection of the evaluation board to your PC. And remember, in this application, the application is configuring the IP address of the evaluation board as 192.168.1.10. So in order to communicate with that evaluation board, you need to configure your PC in the same network. So you have to assign an IP address to your PC's Ethernet port, which is starting with 192.168.1.x. You can give any number for that x other than 10, which is the IP address of the your evaluation board. So I have already done that. I have configured my PC's IP address as 192.168.1.8, and I have already made all the connections. I'll switch on my evaluation board now, and before starting the application, you can start the Teraterm window for observing the serial port outputs. So now we'll start this Teraterm. So we have completed this fourth step of development of the application program and generating the ELF file, that is executable file. Now we are going ahead with the fifth step, that is configuring the FPGA, both with the bitstream file as well as the executable ELF file. So the Teraterm is started. Select the serial port and select the USB to serial converter of the AC701 board and click OK. By default, the baud rate will be set as 9600, which is same as the what we are using for the MicroBlaze. So you need not change any settings. Uh, First, you have to configure the FPGA using the bitstream file generated from the Vivado. So for that, select the Program FPGA tab and select Program. Now the FPGA is configured. Now we can download our application program to the FPGA so that it will run on the processor. So select this application folder and right click on that and select this run as launch on hardware. Now it is launching the application on the processor, and we can observe the Tara term for observing the for viewing the output from coming from our processor. So the application has already started. So as I said, it is configuring the board to the 192.168.1.10 IP address, and it will start the auto negotiation for detecting the operating speed and the full duplex, half duplex configuration, etc. So please wait till the completion of the auto negotiation. Meanwhile, you can open your Windows command prompt, and as you can see here, I have configured my PC's IP address as 192.168.1.8, so that I can try to ping to the board which is having an IP address of 192.168.1.10. So now we'll wait for the auto negotiation to get completed. Now the auto negotiation is completed. As you can see, it has configured the link with 1 Gbps speed. Uh, Now we can try to communicate with the board. So 1.10 is the IP address of the board. I'm trying to ping to the board. So as you can see, it is able to receive the reply from the board, and there is no packet loss. So we have established an Ethernet communication between the PC and the evaluation board, and on the evaluation board on the MicroBlaze processor, your Ethernet based application using the FreeRTOS and lwip IP stack is running, and this reply whatever you are receiving is coming from the lwip IP stack. So that completes the demo.